The title of our proposed project is Practical Waveform Adaptation Scheme for the FMCW radar that can be deployed on modern SDR hardware. So this is basically the title, and this is the proposed work. I will start with my research background. I will introduce myself, a little bit talk on the FMCW radars, USRP 2943, and I would end up with a synopsis of my proposed research. Introducing myself, I have about 17 research articles ever since I did my MS back in 2012. I have about 100 Google Scholar citations. US patent was issued to me back in 2015, which was titled as Radar Deception Jamming Prevention using Biostatic and Monostatic Radars. Apart from that, I have papers in conferences and journals, mostly conferences, related to radar ECCM. A couple of papers on speech signal processing, an odd one on smart transmission grid, on electronic warfare on the radar cross section, a couple of papers in which I have talked about stealth, an odd one. Ever since I started my PhD back in 2015, I have 3 published papers and 2 are under review. One is MIMO radar with orthogonal waveforms, a novel approach for enhanced performance under swirling targets. Apart from that, I presented a paper a few months ago in Germany, and that was titled as Synchronization of Long-Range Widely Separated MIMO Radar Network using GSM Protocol. A paper in IEEE Communications Letter, a hybrid phase MIMO radar, a novel approach with optimal performance under electronic countermeasures. So, all of you know there are lots of advantages of FMCW radar, like ability to measure small ranges with high accuracy, ability to measure simultaneously the target range and relative velocity. Signal processing can be performed on the beat frequencies, so relatively at low frequencies. They're good enough in all weather atmospheric conditions. They have good compatibility with solid state transmitters, and they have small weight and energy consumption. So these are a few of the reasons that we eventually chose FMCW radar as our topic of research here. As I said, I have 2 papers that are under review. I will talk about one of them that has recently been submitted in a journal. The barcode coded FMCW implementation. In this paper, basically, we have tried to show that using the barcode codes and using the barcode codes as a pattern of slope, they can be used for the compression of the bandwidth. So as you know that bandwidth is a very important resource and a very costly resource. So compressing the bandwidth is very important these days, especially for state-of-the-art commercially available SDRs. So in that we have shown that we can get improvement in the spectral efficiency for barcode 13 for up to 47.12% at the cost of very minimal decrease in the range resolution. So as you know that there is a linear relationship between the bandwidth and the corresponding range resolution. But we have shown that by getting this 47% improvement in the bandwidth, we get around 20% of degradation in the range resolution. So after that, we jointly optimized 2 parameters, which were the range resolution and the bandwidth efficiency or the spectral efficiency. So for the barcode coded 11, you can see that there is a maximum spectral efficiency of 58%. So if you are willing to tolerate 39% loss in the range resolution, barcode coded 11 is the best waveform in our case. Nevertheless, the reason to show you all this, and one simulation I want to show you this, that the ghost targets also disappear because of the frequency shift that we introduce in our case. The reason to show you a little bit of background of this paper is that using the inherent nature of the FMCW radars and by manipulating the chip pattern, there is a lot that we can do. So a lot of things can be extracted just by manipulating and by making use of the chip pattern of FMCW radar. So as you know, there are a lot of modulation patterns like sawtooth and triangular and all those things. Nevertheless, there is a lot of room still for making use of the right FMCW chip design for some particular application. SDRs, as you all know, that is a radio communication system where components that have been traditionally implemented in the hardware are instead implemented in the software. So, including this concept in the radar, it makes a software-defined radar. So, the SDRs that are related to the National Instruments and ETS itself are the USRPs. So, the USRPs are the software-defined radios used for RF applications. They can transmit and receive RF signals in several bands, and you can use them for application in communication, education, etc. So they can also be used, especially for FMCW radars. And we are trying to, try to do this. So the type of the USRP that we would be using is a USRP RIO. So the RIO are basically the game changers in the USRP. So it has a very strong field programmable gate array. So if you want to implement some part of our algorithm which requires a low latency, we can implement that code in the FPGA. So yes, we can get the shorter time to result. The USRP that we are using is 2943. It is based on the RIO architecture. It is MIMO, and it has a frequency range from 1.2 GHz to 6 GHz, 7 dBm to 20 dBm power. It has a maximum IQ sample rate of 200 megasamples per second and a bandwidth of 120 megahertz. Apart from that, it has a very strong FPGA, which is of most important concern for the low latency applications. The softwares that I would be using is obviously an LabVIEW and a USRP and a RIO for the LabVIEW FPGA and NI Communication Design Suite 2. Apart from that, we could also use Visual System Simulator, which is also a software of National Instruments. So let's see. All of you know what is LabVIEW, and so since regarding my background, I haven't used the hardware in all of my papers. So only in few of the papers I use the hardware, and none of that use the USRP. So the first step was to learn the LabVIEW and learn USRP for me. So this basically paragraph is the synopsis, and that would even would make it easier for you to understand what I'm going to do here. So modern radar systems are progressively pushing towards the use of adaptive RF front ends, and through the proliferation of accessible software SDR, it is now more than ever possible to develop a complex radar system on a budget. So there has been a wealth of research into what is theoretically possible in terms of waveform design and adaptation, but that has not been leveraged much for FMCW radars. We propose a project that aims to bring the practical and theoretical concepts closer together by developing practical waveform adaptation scheme for the FMCW radar that can be deployed on modern SDR hardware. The work may look at either active FMCW radar waveform adaptation in the presence of interference, or improving detection performance of FMCW radar by exploiting the flexibility in the chip waveform design that I talked about earlier. We are open to applications. We are not confining ourselves to any particular application, but the applications that might be of concern to us can be microdoppler applications, biostatic human microdoppler signatures for classification of indoor activities, human motion detection, and maybe ECCM applications. So we are open to suggestions regarding the applications as well. These are few of the simulations that I have done over the past few weeks. So we have been able to transmit and receive the chip pattern, but my today's talk is not related to showing you the results. Rather, it's about getting the suggestion and tell you what we are going to do in the coming days. So by manipulating the chip pattern, we are getting the different kinds of receive patterns, linear pattern and also the triangular pattern that I already talked about. So this basically is the flow chart of what I'm going to do. So I started with the trends in FMCW radars. I studied a few of the state-of-the-art research papers in the area. I learned LabVIEW. Talking with the USRP 2943 was very challenging at the very start. So I've now implemented the conventional FMCW. So this is the color code, you can do a comparison. So I'm now in the process of making a test bed, and then I will do the FMCW waveform design. The things I intend to do is, because of the title as you saw at the start, that I have to make the adaptive waveform. So this is something that is to be done in the future. Biostatic FMCW is something very important, and then obviously we have to do synchronization for that. We have to do adaptive waveform for the biostatic case as well. We would add the impairment, noise, ECM. Our system should be able to identify that, and then the practical waveform adaptation scheme would be completed. We have to devise the novel algorithms, and yes, in the end, we have to do the real-time implementation of all that. So these are the main objectives: to develop new waveform strategies for FMCW radar systems, to propose new target detection techniques leveraging the sweep frequency pattern in FMCW radars, to propose new adaptive techniques for improving the quality of target detection, to strengthen research activities for FMCW radars with a focus on practical application, validation of the proposed algorithms, and validation of the proposed schemes via SDR implementations. These are the main prime objectives of my 5 to 6 research placement at UCL. Thank you very much.